With Mr. Matthew Rishiger. Today we're going to be looking at the solution to AQA GCSE Physics Higher Paper 2, June 2022. And this is the part 2 of the video, which is going to cover question 5 to 8. Part 1 has already been done, covering the first 4 questions for the paper. The total duration for the paper is 1 hour 45 minutes. To answer all the 8 questions for the total mark of 100. So let's jump in. 5 shows a balance used to measure the mass of 5 tomatoes. So take note of that word there, 5 tomatoes. And then what is the mass? So you can look at the calibration. The subdivision between the 100 is 4. So each subdivision is going to give you 25. So the reading here, the mass of the 5 tomatoes is 425 grams for 5 tomatoes. Now question 1. What is meant by center of mass? The center of mass is a point where the entire mass appear to concentrate, or where the weight appear to act. So that is the definition for center of mass. So for saying this definition, you have 1 mark. Question 5.2, calculate the mean weight of a tomato. So calculate the mean weight of a tomato. The major mistake that most students made in answering this question is using the mass for the 5 tomatoes to calculate the weight. So take note, a tomato, so that is one of them. So what we do, we have the 5 tomatoes, so convert the mass to kilogram. The 425 grams, convert it to kilogram by dividing by 1000. Why do you need to convert it? Because the strength of gravity is given to you in Newton per kilogram. So that your value will be uniform. So to do that, the mass of 1 tomato is going to be 425 divided by 5. So that gives you the mass of a tomato. So if you can get your procedure to this point, so you have 2 marks out of the 3 marks awarded to this question. Then next, use the formula for weight, which is mass multiplied by strength of gravity. Then substitute your value. You have your answer. The mass for 1 tomato is 0.833 Newton. 3. The balance in figure 9 contains a spring that compresses when the tomatoes are placed on the balance. Figure 10 shows the spring with no force acting and with a 6 Newton force acting. So when no force, the natural length of the spring is 5 cm, while the compressed length when the force of 6 Newton was applied is 3.5 cm. So determine the spring constant. So the first thing we're going to do, we have to find out the compression. So the compression is going to be the difference between the compressed length and the original length. So I give a compressed length of 1.5 cm. Determine the spring constant of the spring. So if you want to do that, we use Hooke's law, which says that the force applied is directly proportional to the extension produced. So this extension now is the compression. So if you introduce that with your spring constant K is what we are looking for. So we can substitute the value. So the force that was applied on the balance is 6 Newton, which produced the compression of 1.5. Now the 1.5 cm need to be converted to meter, and you know 100 cm make 1 meter, so we divide the 1.5 by 100. So if you substitute that, you make case solid of formula. So you have 600 divided by 1.5. So solving up to this point, you have 2 mark. Then finish up, you have 400 Newton per meter. So that is the spring constant. Then question 5.4, explain one property of the spring that make it suitable for use in the balance. The property of the spring is the ability to, the elastic property of the spring, that is, once it is deformed, it can regain its structure. So a spring deformed elastically will return to its original length after the force is removed. And or compression is directly proportional to the applied force, because the compression is, which is now used to produce a linear scale. So these are just the basic thing, the two property. So the elasticity of the spring and then the proportionality of the compression. So if you can state those two major property of the spring, so you have the 2 mark awarded to this. So with this, we have finished considering the 9 mark awarded to question 5. So let's go to question 6. All right, this question 6. Galaxy contain billions of stars. Compare the formation and life cycle of stars with similar mass to the sun to star with much greater mass than the sun. This question for 6 mark is a quite technical question. So we are going to look at compare the formation and life cycle of stars. So this is comparison, and in this comparison you're going to be talking about the similarity and you talk about the differences. And the differences, you are looking at it at 2 dimensions. So you are comparing stars that are with almost the same mass as the sun, and then you are looking at those ones with a mass much greater than the sun. So this is the 2-level comparison we are going to look at. So let's look at the comparison. Stars that are the same, almost the same mass as the sun. So now both stars, those ones that are the same mass like both stars, in terms of comparison, whether they are having the same mass as the sun or having mass greater than the sun, both of them are formed from cloud of gas, which is mostly hydrogen, and it does nebula by gravity. So gravity pull them together, the force of gravity pull the dust together, and then both stars, that is both stars and sun, are formed by the fusion of small nuclei, that is hydrogen, to form larger nuclei, helium. So is a fusion. So we have the reaction, the nuclear reaction is the combination of smaller molecule nuclide to form larger molecule. So that is how stars are formed. Then the 3rd level, both stars with mass almost that of the sun and form a protostar. So when the mass of the star is like that of the sun, they will eventually form a protostar. Now, both stars and the sun have a stable period where gravitational force inward balance force outwards due to fusion processes. So you have this 4 level that you can talk about in the formation of star and their life cycle. So these are the 4 areas of similarity you can talk about. So you can mention any 3 out of this. So let's go to the differences between them. We're going to also compare them. Stars that have almost the same mass as the sun, and then you look at the differences between stars that have mass much greater than the sun. So let's look at the differences in their characteristics in terms of life cycle and formation. Stars about the same size as the sun expand to become red giants. So they form red giants on expansion. So why star much bigger than the sun expand to become red super giants? So this is the differences between them. So the star that is the same mass as the sun will become a red giant on expansion, while the stars that are bigger than the sun become a red super giant. So that is one difference between them. So let's look at the second difference in stars based on their size. Stars the same size as the sun will contract and their temperature increases to become a white dwarf, while stars much bigger than the sun explode in a supernova. So the third difference, stars about the same size as the sun on cooling become a black dwarf, while stars much bigger than the sun become either a neutron star or a black hole. So with this, we have 3 levels of differences and then 3 levels of similarity. Each of them that you state will give you 1 mark, which is the 6 mark awarded to this question. The points on figure 11 represent galaxies that are moving away from the sun. Now, what does this figure illustrate? So you have our Milky Way at the center, and then each arrow represents the velocity of the galaxy relative to the Milky Way as they move away from the Milky Way. So you see that those galaxies, when they are close, that means you see that all of them are spreading from a point. That means that at a point in time, all the galaxies started from this point here. And then from here, the Milky Way, they are spreading out. Those ones that are close to the Milky Way have smaller velocity. And then the further they move away, the velocity increases. And then the velocity of those galaxies far away from the Milky Way are moving at a faster velocity. So this one move faster so that there will be no collision, and then this one is moving slower, and then those ones closer to the Milky Way are spreading away at a slower velocity. So let's go and look at the question that we need to answer concerning this related to the Big Bang Theory. 6.2. Light from all galaxies represented in figure 11 is redshifted. Now, what is redshift? Describe what is meant by redshift. Now, you have, so I'm going to use Earth as the example where we'll carry out our observation, and then you have the galaxy close to, so the Earth is located in the Milky Way galaxies. From here we carry out our observation, and then the galaxies are producing radiation, light, because it's a star. So this star is shining from this galaxy. Then as the galaxy move away from the Earth, what happens? There's an increase in the wavelength of the light. So that is what we call the redshift. So redshift is the observed increase in wavelength of light from galaxy as the galaxy move away from us. So that is just the illustration I've given here. Now, explain in figure 11, that is question 6.3. Explain how figure 11 provide evidence for the Big Bang theory. Now, if you look at the diagram that we have here, so you look at the figure 11, the Big Bang theory. If you look at it, what is the point here? It means that the further the galaxies are moving away from the Milky Way, the fastest their velocity become. So we suggest that at the same point in time, you see all of them are spreading from one point, which is the Milky Way at the center, means that all the galaxies started at one point in time. So that is what you're trying to say, the Big Bang. There's an explosion, and then the particles are flying away from where the explosion took place. So that is what this diagram is actually illustrating. And then, because you know velocity is a vector quantity, so you see the field diagram that the longer the arrow implies the longer the velocity, and then the shorter the arrow imply a smaller velocity. So this one is moving slower then compared to this galaxy at the extreme, which are moving faster. All right. Sometimes scientists have to carry out a modification about theories about the universe, give reason why this alteration take place in the theory that have already been postulated. So the most thing we need to know is that there are observation or evidence that does not fit to the current theory. So if there are an aberration, or there is an observation, or there is a difference noticed in the pattern of the phenomena that the theory is trying to explain, then there is room for modification to be carried out on the theory. Question 7. The national grid uses transformer to change potential differences. Okay, now to do that, figure 12 shows a transformer. So we will have the part A of the transformer. So we have the part A, which have 200 turn. So this is the input, which is the primary coil. Then we have the part B, which have 1200 turn. So which is the secondary, is the output PD. So now what happens is that the transformer works by the principle of electromagnetic induction. So since the coil in the primary is smaller than the number of coils in the secondary, we say this transformer is a step-up transformer. So question 7.1, identify the part of the transformer labeled in figure 12. So A is the primary coil, okay, and then B is the secondary coil. So for identify those two parts, you have the one mark out of it. Then the second mark is for identifying the ion coil that is used for increasing the electromagnetic to increase the strength of the magnetic field. So we have that. So the ion coil, identification of that will give you the second mark for this question. So let's see the next question that we have. Question 7.2. There is an alternating input. The input, the primary PD is 230. Determine the output PD, so which is the potential difference at the secondary coil. So when we do that, so you remember that, so we have the ratio of the potential difference, the secondary coil, divided by the PD across the primary, will give you the same ratio of the numbers of turns in the coil. So if you divide the numbers of turns in the secondary coil divided by the number of turns in the primary coil, will give you the same ratio. So you can use that proportionality to get the output PD in the secondary coil. So substituting the value given to us, the parameter, we have this. So for being able to carry out this substitution, you have 1 mark out of the 3 marks awarded. So let's make VS subject to formula. So if you do that, what I've done is that we divided 1200 by 200, which give the green 6. So use it to multiply the 260 volts. So to step it, so this transformer is stepping up the primary voltage 6 times. So and we got that 6 from the ratio of the turns. So for doing that, you have the second mark. Then finish up with this multiplication, will give you the third mark. So with the output PD is 1380 volts. So the voltage has been stepped up from 230 to 1380 volts. The input PD causes an alternating current. Explain why there is an alternating current in the output when the transformer is connected to a circuit. Wow, so what they want here is they want you to explain the electromagnetic induction. So what happens is that the alternating current causes a changing magnetic field around the primary coil. So you have that. And then next, this one will explain the electromagnetic induction. So what happens is that the alternating current causes a changing magnetic field around the primary coil. So you have that. And then next, this one will create a magnetic field that changes direction in the coil. Then this induces an alternating potential difference across the secondary coil, causing an alternating current. So this is a principle of the transformer, which is the principle of electromagnetic induction. So with this, you have the 3 mark awarded. Figure 13 shows a large cable supported by 2 wooden poles. The cable is connected to an electric supply. Then you see the direction of the current. So this is a conductor carrying current in a magnetic field. That is the earth magnetic field. A conductor carrying current in a magnetic field. So you're going to the analysis. Now let's see. There is a force on the cable due to the earth magnetic field when the current is in the direction AB. What is the direction of this force? So let's carry out our analysis. So we're going to use Fleming rule, left-hand rule. So if we use Fleming left-hand rule, so the first thing is we identify, so the first finger will go in the direction of the field. So what you do is that spread out your left hand such that the forefinger, the thumb, and the second finger are spread out perpendicularly, mutually perpendicular to each other. So if you put it, then put your first finger, let it point in the direction of the feed, then position it, and then your second finger go in the direction of the current. So let's do that. Okay, your second finger, position it so that your second finger go in the direction of this current, which is the red, and then your thumb is going to point downward, okay, which is the direction of the thrust, which is a force acting. So you use your left hand rule to identify this. So which direction would the force go? Is going to go downward. So this is using the left hand Fleming left-hand rule. So let's go to the cable experienced a force of 0.045 Newton due to the Earth magnetic field. The magnetic flux density is 60 microtesla, and then the current is 50 ampere. Calculate the length of the cable between A and B. So we force on a cable, that is, the force on the cable is BIL. So the force is directly proportional to the magnetic flux density, is directly proportional to the current, and is also directly proportional to the length of the coil or the wire. So in this case, so with the color coding, we already know the value. So the force is 0.45 Newton. Then the magnetic flux density B is 60. Then you have the current I, which is what, 50 amperes. So we are left with the blue component of this formula, which is the length. That is the next thing we need to do. But one thing you need to know is that we have a small value in the unit, so which is the magnetic flux density. So the magnetic flux density, we have to convert it, remove it here by dividing. So we have this, so it's micro, means you have to divide it by 1 million. So that gives us 60 times 10 raised to power negative 6 to remove that micro there before you carry out your substitution. So let's substitute the values. We have that. Then you make L subject of formula. And then what you do, if you multiply the right hand side out, so you have that is 0.003 L. So you divide, make L subject of formula there. So that gives you the length of 15 meter. So with that, you have the 4 mark awarded to the question. So let's go to section 6 of the question. State one assumption you made in your calculation. Now you go back to the Fleming left-hand rule. What did they say? The wire, the force at right angle to each other, so they are mutually perpendicular. So the current is constant, the cable is straight, the magnetic field is uniform. So that is when this law can be applied. So we just, with all these points, you have looked at question 7, which has 14 mark. So we've been able to look at each of them. A diver brink sinks to the bottom of a swimming pool. So this figure 14 shows the diver brick. So you look at the dimension, is 10 cm high, then it has the width of 10 cm and then the length of 25 cm. So with this we can find the volume of the brick. Then if a swimmer practice diving to the bottom of the swimming pool to pick up the diving brick, so we can also calculate the pressure acting on it. So with that, we know that the pressure acting per unit area, that is the surface, so we need to calculate the base area. So explain why the force on the brick at the bottom of the pool cause the brick to be stationary. So why does it cause it to be stationary? One is that if you look at the brick, why is it that the brick is not floating but it's just at one point? So you have to carry out the resolution. Now the up thrust, which will be acting upward. Okay, so there are three forces acting on the brick. The up thrust due to the liquid where it is submerged. Then up thrust upward on the brick acting normally. And then the contact force on the brick. So we have the up thrust, then you have the contact force. Then we balance up with the weight, which is acting downward. So the weight is equal to the up thrust plus contact force. So that is why, because the total upward force is equal to the total downward force. So they balance off. Now, if they balance off, that means the resultant force on the brick is 0. So that is why it is not moving. So it is stationary. Question 8.2. When the brick from figure 14 is at the bottom of the pool, the top surface of the brick is 2.5 meters below the surface of the water. So we are looking at the depth. So the depth of the brick is 2.5 meters below the surface of the water. Now the force acting on the surface of the brick due to the weight is 637 Newton. The gravitational field strength is 9.8 Newton per kg. Calculate the density of the water in the swimming pool. So this is quite a simple question. There are two ways you can approach this question. So let's look at the first way. The first way, we are going to calculate the top surface area of the brick. And how do we calculate the top surface area of the brick? The top surface area of the brick is multiply the length, which is 25 cm, by the breadth 10 cm. But you need to convert it to the SI unit, which is meter, by dividing 25 cm by 100 and then dividing 10 cm by 100. That gives the total area of 0.025 meters square. So if you do that, now why do we calculate this? We are using the approach of finding pressure. So take note that the pressure is equal to force per unit area, and we were given the force and then we've calculated the area. So if you divide that, you can find the pressure. So with that, we finish up, we get the pressure. Then the next thing you're going to know that the pressure under liquid is equal to the density of the liquid multiplied by the gravitational field strength, then multiplied by the depth. So if we use that, so we're using this formula without understanding that pressure is equal to the density of the liquid, the blue, multiplied by the gravitational field strength, red, then multiply by the depth of under the liquid. So the depth under liquid, so which is the brown. So we are looking for the density of the water in the swimming pool. So we are going to make density, the blue, subject of formula. But let's substitute the parameter that we have, so we can now get so out of these four parameters, we have pressure, green, density, blue, strength of gravity, G, then the H. So the only thing we don't know there is the density. So pressure is given to us. We've already calculated it, which is the last question. Pressure is 25,480 Newton per meter square, or 25,480 Pascal. So let's substitute. If you do that, for carrying out the substitution, you have the 4th mark out of the 6 mark awarded to this question. Then make density subject of formula. So we have that. Okay, then finish up your calculation. That gives you the density of the water. So it's about 1040 kilogram per meter cube. So you have that. So that is the 6 mark awarded to this question. Let's go to the alright, question 8.3. Professional divers are trained in a very deep swimming pool. The density of the water in the pool is not the same as the density of the water treated in question 8.2. The diving brick was dropped into the very deep swimming pool. When the brick is at the depth of 2.5, that is near the surface, the force at the top of the brick is 618 Newton. So now figure 15 shows the diving brick at the bottom of the very deep swimming pool. So how deep is the swimming pool? Now from this dimension here, that is 49.9 meter. So what they want you to do is to compare the force acting on the brick at the bottom, then compare to the force acting on the brick at near the top. So mind you, a critical thinking question that you can do, since the water in the swimming pool have the same density, that means once they give you the density at any point or at any depth, then you can extrapolate it to calculate density at another depth. So that is what this question is all about. So let's go to question, the question that is related to this session, to find the depth. Alright, so determine the force due to the weight of the water on the top of the brick in figure 15. Give your answer to 3 significant figures. So like I told you, that is just a direct proportion question. So what they want you to do is to relate the force at the depth of 2.5 to the force that will be acting on it at the depth of 49.9. So once you have that, so you use direct proportion. Since the liquid is the same, so the force acting on the brick is going to be uniform depending. So the force is going to be proportional to the depth. The force is directly proportional to the depth. So if you have that, so relate it. So then make the force subject of formula. For doing that, you have the first 1 mark. Then substituting, you have your answer as 12,335.28 Newton. Now, but the answer says we should express the answer in 3 significant figures. So express this one, 3 significant figures. So look at the first 3 digits. So you have 1, 2, 3. Then you have 35. So 35, 35 is less the 3. So if you look at this one here, the 10. So we have this. We want to approximate to 3 significant figure. So we have this digit here. We stand for this. So this is 30. So 30 is 3 is less than 5. So we round it down to 0. So 335 is closer to 300 than 400. So we round it down to 300. So the force acting at that depth is going to be 12,300 Newton. expressed in 3 secant figure. So with that, we have the 3 mark that is awarded to the question. So that brings us to the end of the question, the June edition 2022. You are a brilliant student who want to succeed. That's why you are previewing this video. More tutorials solving past exam questions to assist you will be uploaded. Please subscribe to keep up to date. Please kindly like and comment on the video and feel free to ask questions. I will make room to reply you. Thank you for watching.